Okay, welcome back to lectures on the double operatic theory of systems. Right now we're covering some categorical theory of systems. So far we saw a number of notions of different kinds of dynamical system and various other things like labeled transition systems. We'll come back to those later. For now, we're going to really sink in the dynamical systems that are roughly speaking of the form S to Fs. So we saw before that these were called coalgebras. And we're going to sink into things that are of this form, although we're not necessarily always going to express it in that way. But the idea is that such a thing is a map that tells us how to update. So how do we change? Does the state change? Change given how it is. It is. And U is the answer. The answer is U. U, this function. Okay. So, right. You pause it. So, right. It's not, so we saw some examples of this kind of form. So the one being, a discrete time. We saw in discrete space. Deterministic was a function U from S to S. Then we also could see, for example, maybe in the category of sets, but we could also do, for example, in continuous space. But deterministic is the same thing, but now in some kind of category of spaces, and so on for other kinds of space. But also we saw discrete space, or so let's say discrete space, non-deterministic, maybe possibilistic, was U S to the power set of S in set, and then P is the power set. And then we saw this same thing, but now stochastic was U S to the set of distributions. Delta S, well, finitely supported probability distributions on S. And you can actually get this last one to be better if you worked with measurable spaces. You could get all probability distributions, but you have to put the right sort of sigma algebra on the space of all distributions. I'm not going to go into that, but that's there's a number of different categories you could take probability monads on, and it's a very well studied and very interesting subfield of category theory. So there's some good introductions to that by for more on this, maybe I'll say for more see some really great introductions by Paolo Peroni. And I don't know, I didn't prepare any specifics, but I'd say, probability monads is the search term. Okay, that was discrete time. We also have continuous time, and it wasn't exactly the same because we saw that if you had a manifold, something like Rn, then now you don't exactly, the functor sort of f here is like t, but it's not just like hanging out around. The function that you're interested in, u, still does go from s to ts. It's the section of the tangent bundle that gives you the differential equation, an ODE. This is an ODE. But now we also have the condition that that pi u equals the identity on s. In other words, the u sends any state to a tangent vector to that state. Right. But in all these cases, none of these things had any parameters. So an example of a parameterized ODE might be something like, so let's say parameterize parameters. Maybe I'll say a parameter dynamical system, right? So U. That's when we have S to S, right? But maybe we actually take in an extra value here, and so I'll call this P for our parameter space. So now we can see that U S comma P is going to be the next state, and it's going to depend on P. And similarly, we might have a here. I'll take this pi, and then I'm going to just make this expand this sort of diagram here. So I'm just giving myself some more space, but now I'll take S times P up here, and this is going to be the projection here. And I'm going to give this map backwards here called U. And there's this would be this is here a parameterized discrete time system. Also deterministic. Of course, you could just put something on the end here if you wanted it to be non-deterministic, maybe something like F. And then here we have a parameterized, down here we have a parameterized continuous time system. ODE, I should say, parameterized ODE. Specifically, you see now that U, it represents the ODE the same as before, dSdt equals U of S, but now we have this extra variable, P. And then this commuting is just, again, this square commuting is, again, just the sanity check that, in fact, that U of S comma P is, in fact, a tangent vector to S, and therefore a viable way to go. So this doesn't really matter so much when S is Euclidean space, but if you have extra kinematical constraints, so S is a subspace of Euclidean space, then it's very important that in order to stay on that subspace, you need your dynamics to always be tangent to it, so you always flow within it. And that's why we use the tangent space here. So, for example, if S was a sphere, you have to be flowing tangent to it at all times, otherwise you'll leave the sphere. And then that's not a well-defined dynamics on the sphere. All right, so these are two cases of parameterized ODEs. And then, so the nice thing about having parameters is that you can set those parameters. So let me give you a little example here. So here's a simple parameterized ODE. So so here's an EG. Suppose we have a population model. And my population model will be a certain it's going to be, we have our population dp, dt, and it's going to grow at a birth rate of b. So this, if I just left it here, this would be an exponential growth. And then it's going to die at a death rate at d. And now, well, it's still an exponential, but it's either an exponential growth or decay, depending on whether the births outweigh the deaths, right? But here, I'm going to think of here, note that P, this is a state variable. While these two, these are parameters. So this system looks like this. I have a single variable of state, so it's R. And then I have here, again, I'm just putting all the things I need. Now I've written all the S's down because S was taken to be R, the single, S here is equal to P in R, just to give a name to it. And then the parameter space, capital P here, is the space of pairs B comma D of all possible birth and death rates. And so U here, you can see U of P comma B D is equal to that formula. B, oops. dp minus dp. I think I hear some chatter in the back there. Okay. Right, so that's what that looks like. Maybe I'll just put this underneath here. Okay. So now, suppose we had two of these. So suppose we had two populations, right? So I'm going to write them, let's call them, it's a classic here, foxes. So df dt is equal to birth rate of foxes times the number of foxes minus the death rate of foxes times the number of foxes, and rabbits. So they're both isomorphs of the above system of equations individually. They both have the same form. But now I can imagine that if these were my equations and I wanted to consider them together, it's as if the foxes and the rabbits never interact, right? But if the foxes eat the rabbits, right, then the number of foxes that there are is going to be, proportion. The number of rabbits eaten is going to be proportional, let's say, to the number of foxes that there are. So we might add some coupling laws. And so those coupling laws might say, like, for example, the death rate of rabbits is equal to some proportionality constant times the number of foxes. And similarly, the more rabbits that the foxes eat, the more energy they have, the more they're able to lounge around and have some fun. So we might also say that the birth rate of foxes is coupled by some proportionality constant to the number of rabbits. Since the more rabbits there are, the more the easier it is to eat, the more time they have for fun. So when we take these together, we get a coupled system. And it is a single system. I will note here that these are sort of two separate systems, plus some kind of coupling law. And they give us a single system, which is now a two variable system. So I'm going to write it like this first. I'm just substituting in what we know. Right? And that's our single system of equations. But one thing I want you to remember is we're always writing these system of equations as vector equations. So I could write this as a single equation concerning the vector fr tt. And now I have to give you a vector law. Maybe I'll make it in vector notation. Although it's really a point, not a vector, but I don't know why I read it so small, but the point is you can pack it up into a single equation, but now you're just operating on pairs. So let's see how this goes here. Right. So now what you can see is that the main point of having parameters for systems for us is one thing is that, like, when you're running a model, often you're modeling a situation. You don't always know in advance exactly what all the specific details are, or more generally, you want to express the model in some degree of abstraction so that it can describe multiple different particular arrangements of the world, and then you can make, differential, or not in the sense of calculus, but in the sense that you can look at the differences you get by plugging in different parameters and seeing what you get. So even these proportionality constants we might decide to take to be not constant, but in fact further parameters that we might set to get a family of models, right? But another thing you can do with them is once you have parameters, you can allow them to be set functionally by the result of the states of other systems, and that's what we've done here. So these are, we're setting parameters as functions of the states of other systems. And that's not the only way. That's not the only way to set parameters, or to couple systems, I should say. That's not the only way to couple systems. And we'll see a bunch more as we go on. But this is the one I'm going to focus on today. So this is a fun coupling situation, but in order to express the category theory of this, I'm not going to start with ODEs, because ODEs have this special extra thing going on. This the fact that they always need to whoa, what have I done? Can you pause it? Okay, excuse me. So now what I want to do is step back to the discrete case and look at how that one works, because it will be a little easier to understand, because we don't have to keep track of these dependency relationships between the updates and the parameters and the given states we're in. We can just focus on something that is sort of straightforward like this, a single function. So let's describe that. There's a notion. So there's a notion here of Moore machine, which is going to be very relevant. This is a kind of abstract machine due to Moore. It's a sense, in the same sense as like a Turing machine is an abstract machine, and so on, a post machine. And you know. So what is a Moore machine? A Moore machine here consists of sort of, it's a parameterized, so is a parameterized discrete time, discrete space, usually deterministic, but not necessarily, dynamical system with observable variables of state. So what that means is it consists of a set S of inputs, of states, to a set I of inputs or parameters, a set O of observations or outputs, and then two functions. And so two functions here, which I'll write like this. So first thing is something that we've seen before, is this function. So I'm going to give the deterministic one here. Of course, the way you make this non-deterministic is you just, put f in here. Put f there if you wanted. We'll come back to that. Right? So this is the update function. And then also you can have an observation or an expose function / observation. So the way we think of such a thing is we imagine it being an abstract machine that lives in a little box. So the little box has an input wire on which elements of the set I flow, and it has an output wire on which elements of the set O flow. In the box, which we can't really totally see in, is the box is in a set of states, S. So now when an element I flows into the box and the box is in state S, together we get An element, well, first of all, we get the element ES of its current state. We read it out right away. We observe the current state. And then we also take the I and the S, and we take them both, and we give ourselves USI, which is our new state. And so in a sense, such Moore machines can act as ways to transform elements of I into elements of O. You can think of them as sort of a parameterized function from I to O. But it's not exactly the right way to think about them because they don't super duper behave like functions. For example, they don't really form a category. Now, there's another very, very similar notion of machine, which I might come to at some point, called a Mealy machine. And those do form something like a category, and they work great like that. But I'm going to do Moore machines because this formalism works the most similarly to the ODE case. So that'll keep us in touch with a lot of modeling in practice, which is just done with systems of ODEs or similar such things. Okay. So that's how we think of such a machine. An example of such a machine might be sometimes they're written. Oops. Sometimes they're written as these as labeled transition systems. Although not every labeled transition system gives a Moore machine. But suppose we have two states A and B, and we can write these transitions here, 0 and 1. And then this one here will be 1, and this one here will be 0. So what this corresponds to, this picture corresponds to as such a machine, is that S is equal to the set of A and B. I is equal to the set of possible inputs, which here is 0 and 1. And well, I haven't said what O is. So maybe I can give a little dropout here and say that O is something like, in this case 0, and in this case 1. O is also 0, 1. And now that picture there says that U of A0 is equal to B, and U of A1 is equal to A, and U of B0 is equal to B, and U of B1 is equal to A. In fact, I think if I want this to do something cute at the end of it, I might switch these. And then I just switch them over here. Right. So now this is a nice flip-flopping machine. So if it reads in a 1, it changes state from A to B, and if it reads in a 0, it stays in the same state. And then you can see also we have the two readouts here, which says EA0 and EB is 1. So now we can think about what happens if we send in a bunch of inputs, right? If we started at state B here, or if we started at state B, and we read in a 1, we would go to A, and we would output a 0. But if we read in then another 1, we'll go back to B, and we'll output a 1. And in general, if we read an even number of 1s, we'll end up outputting a 1, and if we read an even number, an odd number, we'll end up outputting a 0. So this machine you can think of as a way of classifying whether the inputs have an even number of 1s or an odd number of 1s. So that's the way you normally think of this, as sort of a finite state machine. I'll note that what's normally called a deterministic finite automata is a finite Moore machine where O is equal to 0, 1, the Booleans. In other words, we just have the output is whether or not you accept that state. And then it usually asks for a starting state. I'll note that often the machines are said to come with their starting state. I'm not going to keep them with their starting state. We're going to let them start anywhere they want, and then we'll just say that what they do, given where you started, is a little different. For example, if you started this same exact machine at A, it would now give you a 1 whenever you read in an odd number of 1s. So to understand a machine as a question, like as a way of answering a question about its input, you need to include the starting state. But for us, we're gonna see it as a model of a certain kind of system that's happening in the world. This might be a model for a light switch or something. Okay. Not all label transition systems give us more machines because you need U and E to be, well, E, first of all, doesn't really exist in the label transition system formalism. And U needs to be a function. So we need the labels, we need every node's out degree to exhaust all the labels and only exactly once. Although, of course, we could get non-deterministic Moore machines if you take a more general approach. Okay. So, right. So now what we can do with Moore machines, if you draw them as boxes like this, draw them as little boxes, you're quite tempted. All right. You're quite tempted here to try to just pipe things through. Yep. So if I can put something in here, which I'll do as a little triangle, if I could put something in here, some function f, where f went from O1 to I2, in other words, I had some way of producing from an O1 and I2, right? Then I should be able to sequence these machines. So I'll put all of this in a box. And if I black box this should be a sequenced version. We could call it S1 dot FS2, something like that. They're sequenced with this mediating function f. Of course, if S1 actually outputs directly into the set I2, we don't need the f, but they're in general. So how does that work? Well, what is the combined state of this combined system? So the state of S1 dot F S2 is, well, it's a pair of states in S1 and S2. So it's S1 times S2, state space. Right? So in the big box, when we peek into it, we see we have two little boxes. Each of them is in a state, so we need to record both of those. So what is the combined update? Well, now, so the combined update so let me, I guess let's do the combined observation because it's going to be easier. As you can see here, what is the ultimate output of this combined system? It's O2. So the ultimate, so the ultimate the input here is I1, and the output here is O2. Together, by the way, the inputs and outputs, and I should have said this above, these are called the interface of the Moore machine. Okay. Right? So the combined observation is as a function E combined, and it's going to go from the state space, the combined state space, and it's going to go to the output. And it's pretty clear what it has to be, right? By looking at the picture. The output we actually get is whatever S2 outputs. So E dot F of S1, S2 is going to be equal to E2 of S2. Okay. Or more categorically, we have S1 times S2, we project onto S2, and then we do E2 onto O2. This composite. The combined update, on the other hand, well, what is the input for this combined system? It's I1, right? So here, it takes in S1, the state of the combined system, together with an input for the first system, and it's got to give us a combined state of the two ones, right? So if we imagine what happens when we run this, if a little input comes in over here, we first hits this first system and it updates it. And then that system outputs. Well, then actually I'm going to go ahead and say that actually this observation, the wire here is sort of considered in all of these. The timing of this is perhaps a little unintuitive, but this is the way it sort of works out quite nicely, categorically at least. The timing of this is a little unintuitive. It's not so much then. This system is already outputting, and that output is already loaded in for this system. So the systems the observations are something that are made of the system now, not after it updates. Right? Just to say, if you want to observe the system after it updates, you let it update and then you observe it. That makes sense. So, okay. So what we're going to do here is u dot f of S1, S2, I1, I'll say. Well, what do we do? Well, we know how to update the first one. It's U1, S1. Okay. Right? But then how do we update the second one? Well, the second one needs an output from the first one. So we can do that. We can update the second one, and we're just going to take the output of the first one, E1 of S1, and we're going to pipe it through F. I think that's enough parentheses. Okay, and that formula there represents the combined update of these two systems. So I want you to note that it takes 2 time steps to propagate through it in this formalism. So this is essentially the main reason that these don't form like a category. Because there's no way to have something propagate through a combined system of this form in a single time step with this formalism. This is fixed, if you consider it a problem, by using more Mealy machines, where you can directly pass through to the output, and therefore you sort of circumvent this 1 time step delay issue. But here, these systems work more like they end up working very nicely, more like the ODE. So I'm going to keep talking about them here. Okay. So there's other kinds of ways we could. So this is a kind of coupling. It's a little different than the Lotka-Volterra we saw, but it's sort of similar. In that we've set the parameters of one system, namely the input for system 2, according to as a function of the observation we make of the state of system 1. Okay. So I suppose that okay, I got to talk about more machines. I'm going to talk about more kinds of coupling we can do. So one fun kind of coupling, one thing we can do is we can consider more machines to take in multiple inputs and give out multiple observations. So when we draw this, it's really just a syntactic sugar for this. In other words, a system here where multiple inputs and multiple outputs, it just takes in both those inputs simultaneously, and it gives both these observations simultaneously. In other words, this is a series of functions U from S times I1 cross I2 to S, and E from S to O1 times O2. In other words, so in this U doesn't break apart because it's something like S, I1, I2. You need both those informations to get into S. But in here, we actually have E1, which goes from S to O1, and E2, which goes from S to O2, and they can be sort of decoupled at will. They're the projections, the 2 coordinates of that observation. When you have something like this, you can do other kinds of composition. So here's a fun one. You can end up by feeding a system into itself. So suppose that this is I, and this is O, and this is, let's say, M for the middle. What would this combined system that I'm going to put itself in an entire box be? Well, its state space is still just S. So the states is just S. The interface now is I and O. That's how I'm going to write these pairs. But now the update here, well, it takes in just an I and it gives me an S. And the expose takes in an S and just gives me an O. So how do I make this new update? Well, I'll call it update bar to distinguish it from the old one. The new update takes in an S and an I, but I somehow need I need something else because I need the original system took in also an M. But luckily, I actually already have an element of M because I have my other expose. So it's going to be U, the original, and I'm going to take in the expose valued 1 of S and the I. Because this is the first expose here, first observation here, the I. And now, similarly, E bar of S, again, that's just going to be E2 of S, the one that already was piped out to O, which you can just see in the picture. Okay, and so now you see that this is sort of why we introduce in a way these delays is so you can have this well-defined thing is you can read out the system right away. Because you couldn't update this system until you actually had something, if you will, flowing along the wire M. Okay. So we can combine these two, right? There's no reason that we couldn't, for example, look at this system here and suppose that S was itself built out of a composite, right? So I can nest this. So here's my S. Suppose I have my input here, it comes in, it goes in here, and it goes in here. These are connected by a single one here. And these loop around like this. There's no reason we couldn't have nested composites, right? The formulas will still work at any stage. And one thing to note about this is that if you write down all these weird ways to couple these more machines using these wiring diagrams, these kinds of things are called wiring diagrams. And to distinguish them from various other kinds of wiring diagrams, I'll call them directed wiring diagrams, and we'll give a really nice categorical story of this very soon. So one thing to note about wiring diagrams is we could do this in two steps, right? We could define S by writing down the inner wiring diagram and then do the above diagram to get using this formulation up there to get the new combined thing. Or we could flatten the wiring diagrams by just erasing the middle box. And then do this wiring diagram, which is more complicated, all in one step. And we'll get the same resulting system. It sort of should be obvious from how we went around turning these wiring diagrams into these formulas by just reading out which inputs go to which outputs. But it would be really nice if we could actually define a mathematical system for doing this, and we didn't have to rely on looking at a picture and writing down by hand a bunch of formulas that are a little bit inscrutable, right? Like this, what? I mean, it's clear once you know what you're doing, but wouldn't it be nice if we had an abstract algebra for doing this? I think so. Okay. So now we're going to talk about lenses. So I'm not going to give a real history of lenses. They were developed in computer science in order to solve a problem there known as the view update problem. And the idea of view and update is very similar to how we're using lenses here, because we have these two functions. which I called update and expose, but I could have called update and view. It's the observation and the update of the system. But we're not using it the way the computer scientists will use it. And in fact, there's a lot of things that have been called lenses in time. And there's not even standard terminology for what to call the various things that have been called lenses. So I'm going to use a notion of lens that is sometimes called a polymorphic lens, a bimorphic lens. And these are, in fact, the lenses in Haskell. If you are familiar with the Haskell lens library, we're not going to present them the same way that they do. Or the Haskell profunctor lens library, we're not going to present them in that way either. But the underlying data is equivalent. And so we're going to be doing those kinds of lenses. If you don't know what those are, don't worry about it. It's not important. So a lens is what's known as a bidirectional transformation. And it has two sorts of directions here. So a lens is something that has a domain which consists of two sets. The bottom one we call the pass forward, and the top one we call the pass back. A lens itself is a pair of maps between these sets. I'll draw it like this. I will note, by the way, here and for the last time, that my conventions on whether the pass forward or pass back goes on top is different than much of the computer science literature, but it is well motivated by the situations I'm going to be using them in particular the ODE case, where the pass back has a type dependency relation on the pass forward, and it sort of lives as a bundle over the pass forward. And so it's over, so I draw it above instead of below. Okay. So it's a pair of functions, which I'll write f and f sharp. And what these two functions are is f is the pass forward function. It goes in the direction of the pass forwards, a plus to b plus. And then f sharp is the pass back direction. It goes from a plus times b minus to a minus. So that's a little weird, but the idea is that this is a bidirectional transformation. You go forward in the pass forward and you go backward in the pass backward. The only thing that's special is that when you pass backward, you're allowed to use this extra variable of a plus. Yes.
Oh, 5 minutes.
Oh, okay. Right. So the thing I want you to know is note a Moore machine is a lens. UE. Why? Well, simply a Moore machine is exactly two functions, E S to O and U S times I to S. And if you look, you'll see that that's exactly the same form. But that is not why, that's not so important of an observation, except that lenses have a lens composition. So, but here we have lens composition. And what we'll see is that lens composition gives us a really nice way to describe the various couplings of our Moore machines. And then we'll bring that back later to couplings of the ODEs. And we'll describe how that relates to wiring diagrams. So lens composition here. So given lenses like this, their composite is a lens like this. And it consists of two functions. First, in the pass forward direction, it's quite easy. We just keep going forward. But in the pass back direction, we have to go A plus times C minus, and we somehow have to get to A minus. So what we're going to do here is first, we're going to duplicate the A plus. I'm going to need more space. Boop. First, we're going to duplicate the A plus. Then we're going to map that second A plus to B plus using the push forward. Now we have B plus times C minus next to each other. So we can use the push back there to get a B minus. And then finally, we can use the pass back of the second direction. So in formalism, for variables, this top thing looks like this. It is the function f sharp of, and then where I'll take my elements here, a plus comma c minus, two elements. F sharp of a plus comma g sharp of f of a plus comma c minus. That's the formalism. It's a little weird. It's a little weird. Now, it's I'll maybe leave it as an exercise that this gives you a category. Gives you a category of lenses. And it will be lenses in set because we did this with sets. But as you can see here, nothing really was special about sets. If you have this Cartesian product, you can do it no matter what. And it needs to be a Cartesian product. I'll talk more about this in a future. It needs to be a Cartesian product, at least for the pass forwards, because you have to take the duplication of the pass forward direction. Okay. So this forms a category, and that's going to be called the category of lenses. I think next time we'll look at how lens composition can give us the coupling of systems. But as a peek to that, note that the Moore machine is a lens into I/O. So if we have any other lens out of I/O, we can compose it, and we'll get another Moore machine. Because what makes a lens a Moore machine is just that its domain, the back part over here, is of the form SS. And that doesn't change if we compose on the right in here with another lens. So that's how we're going to couple Moore machines together using lenses.